So we've been talking about electron configuration. Are you guys feeling pretty confident about that?
Yeah.
I'm okay.
Somewhat.
Somewhat, okay. So we're going to kind of test out that theory a little bit. But let's go ahead and we'll start with the slides and then I'll work our way to the periodic table here. So. This afternoon's class, I mean this, I guess early afternoon, you guys are evening now. So the afternoon class was on point today. They were just like on fire. Okay, so there are a couple of things that you guys want to keep in mind. Basically, I've been talking about the different orbitals, right? And so you guys know that for every orbital can only hold 2 electrons. So we know that the S, let me type this. The S subshell oops. Okay, so we have the S subshell. It can hold how many electrons?
2,
Okay, so how many orbitals must it have?
4,
2.
Okay, if it can only hold 2 electrons, and you can only have 2 electrons in an orbital, how many orbitals must it have?
1.
1.
Mm.
Okay, so we were brushing off those cobwebs. You know, that weekend, you guys turned up a little too much. I heard it was good, so then that worries me a little bit. Maybe you guys partied a little too much there. Okay, so what's after the S? We have
P.
and then how many orbitals would that have?
3.
3.
And then how many electrons can that hold?
6.
6.
Okay, and then after the P,
D.
D.
how many orbitals?
5.
5.
How many electrons?
N.
Okay, then we have
F.
how many orbitals?
7.
And how many electrons can it hold?
14.
Okay, so if there was a G, then how many orbitals would you expect that to have?
9.
9,
It would hold how many electrons?
18,
And if there's an H?
11, 22.
How many electrons? Okay. Okay. So now the thing about these orbitals, right? Say you have an option. You could either have no electrons there, you could have 1 electron there, or you could have 2 electrons there. But you can't have more than that per orbital. Okay. Now subshells, we're talking about in a subshell, like in the P subshell, there are 3 orbitals. So it can have a total of 6, 2 in each one at the most, right? Or 1 in each one, right? You guys understand that? Yes, no, maybe. Okay, so that is called Pauli exclusion principle. Okay, so the periodic table helps us understand that arrangement. We've already talked about it. That was the first thing I threw at you. And now here's this beautiful diagram that basically shows you exactly what we had been talking about. And so let's take a look at an actual element and we'll determine the. So here's our periodic table. So let's take a look at an element. So let's do something like platinum. Where's platinum located at?
78.
78. Okay. So we had talked about that core and what we call valence electrons. So we said that the noble gas that would be before that element that we're looking at is going to be our core. So we'd write platinum. And what would be the noble gas that would be before that?
Xenon.
Okay. Okay, so if we start at xenon and we work our way to platinum, what would be the next electron configuration for it? The next thing that goes there.
6.
6. Maybe
6s2.
6s2. Okay. And then
D.
F.
5d.
ID.
okay, so what I recommend is, so xenon starts at 54. That's the atomic number for xenon. Then we went 55 and 56. So that accounts for those 2 electrons there. So if I'm following that, where is 57?
Oh, 4f.
4f. Okay, that is correct. So it'll be down there at the 4f. And it's completely full. Right? So we're going to go all the way to how many does the F orbital hold?
14.
14. And then we know that this very last one, that's a D, so that we have to go back up to 71, and then we go back up to here. So it's D 1, 2, 3, 4, 5, 6, 7, 8. So it would be 5 D8. Okay.
Okay.
Piece of cake?
Can you do another one?
Yes, we can.
Wait, can you go back? Why was it 5? Wouldn't it be 6 D8? Because it's on
Nope.
the 6th row.
It's on the 6th row, but remember, this guy starts at 3D, right? That's 3D. This is
Oh,
3D,
okay. 4, 5.
and then this is the 5D, yeah.
Okay, okay.
Okay, so let's see. Let's do Lawrencium. So where is Lawrencium located at?
103 or LR.
LR. So you said 103. Okay, so we're going to do LR. Okay, so what would be the core noble gas?
Radon. Radon.
Radon.
Radon.
Okay, so Rn.
Oh.
And then
Let's see.
7S2.
7s2. And then
5F14.
right, 5f.
14.
And then
And then 61.
that is correct. Good job. That was impressive.
Can you go back to the 5F14? I get stuck right there.
Okay, so if you follow the atomic numbers, right? So radon starts at 86. Then we go 87, 88. So that would be our 7s. And then where's 89 at?
Way at the bottom.
At the bottom, right? So we know that this is the 4f.
And this
So then what's after 4f? That has to be 5f down here.
5F.
So 5f14, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. And we know that both of these are actually in the D. This would be in the 5D. And then this guy would be in the 6D. And there's only one, so 6D, 1. Because you guys remember what this really looks like is like this. Give it a second. Flex. Okay, so I'm going to use a different color. All of these down here. Come on. Okay, all of these guys down here, those are our S, right? Here are our D. So you see these guys are really in the D, right? So just because we don't have paper big enough, you know, to sit there and print out, I guess we do, but it'll be so tiny that you can't really see it that well. So they try to make it a little more comparable to put it on an 8 by 10. And so that's why we do this.
That slide you just showed us, the table according to atomic sublevels, really helped.
Yeah, because it does make sense now. You can kind of see it, you know?
Yeah.
Okay. Questions?
No.
That's good. I like when there's no questions. Good. That means I can keep going and adding more and more information. Right? Okay, so now let's kind of clean this up a little bit. Okay, so as I said, the core, right? The core is kind of like they're saying that those electrons that are all in that core are locked up, right? We don't want to use those for anything. We want to kind of save those. Those are for that atom itself. You want to save it for the atom. But these other electrons, these guys would be considered your valence electrons, sort of, okay? Okay, so these guys can be used for reacting and other things, okay? So this guy's your core, so these are going to be unused. But these guys are going to be considered like valenced electrons, okay? So let me give you a little information. It's going to kind of blow your mind a little bit. So we have the lanthanoids, the actinoids, and those transitional metals. These guys here, all these guys in the middle. Now, these guys are kind of like a hot mess, right? So because they have the D and the P orbital, I mean, the D and the F orbital, their valence electrons are going to be a little bit different than others. And so because they're kind of a little different than others, it's going to be a little bit harder to kind of to scope out that valence, right? And so the valence for them are going to be a little bit different than, let's say, the valence for our non-metals and then our alkali metals. So these guys over here and these guys over here. These guys are going to be easy because really they're just like S and the P orbital, right? That we're working with, right? S and P. Where these guys are the D and the F. So they make things very, very complicated. So those guys are all kind of called metals because of that, because they're a little more complicated. They go through types of changes, okay? So these guys, they form the ones that are in the S orbital and the P orbital. Their goal is to try to get to their octet, having that outer shell completely full, right? So basically, you're going to either try to have no electrons around you, or you're going to try to have 8 electrons around you. 8 meaning your octet in the outer shell. Okay, not 8 total electrons, but 8 valence electrons in the outer shell, or no valence electrons. Because if you do that, then you're stable. Okay. And so let's say, for instance, we're looking at lithium. What is the electron configuration for lithium?
Two.
Helium,
So we can write it as just helium and
right? And what?
2s1.
1s,
2s.
2s. Sorry,
2s. Yeah. 2s1.
That's it.
Right?
2s1.
Okay, so we can write it as helium 2s1, or we can write it as 1s2, 2s1. Both of those would be correct. Right. Okay, so this guy represents the core. This guy represents our valence electron. How many valence electrons does helium have?
1.
It has one valence electron. Okay, so since it has one valence electron, and the goal is to try to be like a noble gas, it could be like helium, or it could try to gain 1, 2, 3, 4, 5, 6, 7, and be like neon. Which one do you think it would want to do?
Be like
Like the noble gas.
It's going to try to be like helium, the noble gas helium, because all it has to do is lose one electron rather than trying to gain 1, 2, 3, 4, 5, 6, 7, which would take a lot more work. Okay. These atoms are very much like us. They don't want to do any more work than they have to do. Right? So in this case, this guy would lose one electron and become just like helium. So then we write it as just like this. Okay, so it loses one electron, so it would have a plus charge. Okay, because electrons are negatively charged. So this guy's called lithium, in this case, would be called an ion. And to be specific, it is a cation, which is a positive ion. Okay, cation, positive. Okay, you guys don't get my joke. Huh?
I get it.
Meow, meow. Ow. Okay. Okay, but it is really called a cation. Okay, so cations are positively charged, and then let's say we have, let's say chlorine. So what would be the electron configuration for chlorine?
neon.
Neon.
Okay, so neon,
3, 2s. I'm sorry, 3s2.
3s2. And then
3p6.
5.
3p5.
Well, 5.
Okay, so how many electrons does it need to be like argon?
1.
It needs to gain one electron, right? So if we give it that one electron, it's going to be just like argon. So we can write it like this, or we could write it like this. Okay, so since it gained one electron, it has a negative charge because it gained an electron. So this guy is called an anion. Okay, so a negatively charged ion is an anion.
Sorry, Dr.
Okay.
Henry. I was distracted by my son when you were explaining lithium. For
Uh-huh.
lithium, we removed one,
Yes,
and that's why it's the positive ion. And
that
then
is
for
correct.
chlorine, we added, and that's why it's a negative.
That is correct.
So,
Okay.
okay.
Okay. So again, the number of valence electrons. The valence electrons allows, those are the guys you're going to be using. So to be stable, to kind of get like the noble gases, these guys have the option. They could either lose electrons, they could gain electrons, or they can share electrons. Okay. So if you lose an electron, right, you're going to be forming an ion. If you gain an electron, you're going to be forming an ion. So ions come together to form what we call ionic bonds. We'll talk about that next week, or no, probably this week on Wednesday. Okay. And then if we're sharing electrons, then that forms what we call a covalent bond. And we'll talk about the different types of sharing later on. Okay. So you guys with me so far?
Yeah.
Yes.
Okay, so now I'm going to test this out, right? So it's going to be important that you understand when we're losing electron, right? So this is kind of easy because lithium only had one electron to take away from it. Now, normally when you're taking away electrons, when you're removing electrons, right, you always want to take away from the highest energy level, right? So this was easy. The highest energy level was 2. We don't want to mess with the core, right? So we take away from this guy first. Okay. So now when we start talking about these transitional metals, we'll start off with one of the ones that we have up here. Let's say we had, you guys mind if I erase a little bit to give me, get rid of this lithium.
Dr. Henry, does this only apply to the lanthanoids and the actinoids?
It actually, yes, it mainly applies to those guys. However, in all honesty, it kind of applies to everything
Okay.
generally, but it's more apparent with those guys. Okay. So, and then also the transitional metals. So it's transitional metals and the lanthanoids and the actinoids. Okay.
Thank you.
So let's say in the case of platinum. So if we went platinum, now these guys could have multiple charges, different charges. That's partially why it makes them a little complicated. So if we said platinum 2+, so that means how many electrons are we removing?
2.
We're going to be removing 2 electrons. So in this case, if we remove 2 electrons and we want to take from the highest energy level, where are we going to be taking from? Which one of these are the highest energy level?
The F.
The 14?
Is 4 higher than 6?
Oh.
Oh, okay.
So remember, this refers to the energy level that it's at, right? So who are they going to take away from first?
The S.
So yes, that's right. So we're going to take away from this guy first. So we're going to remove 2 of those guys. And then so we're going to be left with 4F14, 5D8. Okay. So if we said we want platinum +4. So how many electrons are we removing?
4.
We're
4.
removing 4. So in this case, again, we're going to take away from the 6s, and then we're going to start taking away from the 5d. So then that would be the xenon, or F14,
5D6.
5d6.
Is that because we took out the 6s2, so now we're only taking 2 from the D?
That is correct, because we're taking away a total of how many?
4.
4, right? And that'll count for the 4. So remember, this tells me the number of electrons. This tells me that energy level.
I have a question. In what scenario would you be removing these electrons? Like for what reason?
To react with stuff.
Oh, okay.
Yeah, that's the whole purpose. Remember, how can you become more stable? Well, if you're these guys, all of these other guys, except for the noble gases, the only way that you can become stable is by reacting with other things. And so either things are going to be taken away from you, or things are going to be given to you. Now, all metals always like to be kind of positive, right? So non-metals like to be negative because they're kind of closer to the noble gases. The metals are kind of farther away from the noble gases. So it's easier for the metals to have things removed, where non-metals, it's the other way around. Does that make sense?
Yeah, that makes sense.
Okay. Okay. So do you want to try one more?
Yes.
Okay, so let's do LR 3 plus. Okay.
So we'll take away from the 7s2,
Okay.
two
So
of those.
we'll put our core in first.
Mhm. Rn.
Okay, so we're going to take away from this guy. And
then we'll take away. So we'll only be left with 5F14 because we're going to take away, since we need 3, we're going to take away from the D.
that is correct. So we'll only be left with 5F14.
14.
Okay. You guys get it?
Yeah.
Sort of.
Oh, okay.
Okay, so let's do one more because I get excited about this. This is really my wheelhouse here. So we'll do tungsten, and then we'll do tungsten 3 plus.
So
E.
Okay, so what would be our core?
Xenon Xe.
Okay.
And 6s2. Then 5d 14.
4F14, no?
You said 5D? Yeah, there we go. Or F14.
Or
And then 5D what?
3?
Now remember, this is a
4.
space here. 4. Yeah. Okay,
Oh, so we
fix that S.
count the space as well?
Yeah, that space counts as a spot. Remember, the LU and the LR are actually in the space between that 56. So
Okay.
they're actually in that one spot. But you have all of these guys that would be in front of them.
So you don't count 71 for that one?
No, you do count 71, right?
Oh, okay. Never mind. I see. Yeah.
I know that's the hardest thing for students to remember, is that the periodic table really have these guys inserted, so it shifts everything. Okay, so if we're doing tungsten 3 plus,
It would
Would
be
it be
Or F14
for F14?
or ZXE and for F14.
okay? So you said it's going to be XE
Mm.
for F14,
5D3.
And 5D3?
5D3.
So are we going backwards?
Yeah, in a sense, yes, you are.
Yeah.
Because you're going to go, but you always remove from the highest peak. Because remember, you're going backwards because you're losing electrons, right? You're not putting electrons in. And so all of this is called electron configuration. So you're going to be moving electrons, right? So if this is a 3 plus, you're losing 3 electrons. And you're going to take away from the highest one first. And then you start with the next level, the next one, the next highest. Does that make sense?
So I would go from that element, the tungsten, back to the xenon.
Well, it's not that you're going to xenon. You're just because the core, I mean, the number of protons are still the same. The thing that you're changing are the electrons. Does that make sense? And so that's also what makes it positive, because you have more electrons than you have, I mean, you have more protons than you have electrons. Because remember, an atom is made up of protons, neutrons, and electrons. All we're doing is removing electrons. Okay.
Okay.
Dr. Henry, can we do one more? Sorry, I'm just getting home from work.
Yeah, we can do one more.
And the question for this would be, was it find the electron configuration for PT2 plus? So would that be like one of the questions?
Exactly.
Like the homework, but would there be another type of question that, you know,
Yeah, there will be, but we'll get to what other type of question you may run into.
okay.
Okay, but it's going to say electron configuration.
Okay.
Okay, so let's do, I'm going to erase this now. Okay, so let's do manganese. So find electron configuration for manganese and manganese. Let's do 3 plus. Okay, so where's manganese located at?
18 or shoot, manganese, sorry. I was
25.
25.
Okay. So what is my core?
Argon.
Argon.
R.
Argon.
4s2.
Right.
Okay.
(3D5).
Right.
Okay, so then what would be manganese 3 plus?
3D4.
Piece of cake?
Yeah.
Okay,
Yes.
so let's see if we can do one that's a little more challenging, and then we'll move on. Okay. EU. So what would be my core?
Xenon.
Xenon.
Then
Mm,
6s2.
S2.
Okay, 6s2.
And then 4f.
Wait, I'm sorry. I have a question. Why is it
7.
6S?
Okay, because where is EU? Who asked the question?
Me.
Who is me? Okay,
Mhm.
do me a favor. Circle where EU is at. Okay, so that's where EU is located, right? So if we start at the nearest noble gas, or the noble gas that is before that one, so look at the atomic number, it's 63, right? So we know that it has to be xenon that is the first noble gas, right, before it.
Oh, okay. Yeah, I saw what I did wrong. I looked at the. Okay, sorry.
Okay.
Yeah.
Well, that's all right. Okay, so then we go down, and then we're at the 6th energy level. So this is 6s, right? So 6s2. And then where do we go?
Oh.
4f7.
Right. So that's 1, 2, 3, 4, 5, 6, 7. So 4f7. Okay. So if we're going EU2 plus,
Just xe.
Oh,
And
sorry.
4f7. So on this next one, are you going off of the one you just did or the original?
I always use the original because it makes
Okay.
it easier.
Okay. So then 4f or xe, yeah.
And then we're left with 4F1
4f3.
because it's +6, right?
Yeah, it's +6. So we have to remove 6 electrons. We're not moving 6 electrons from this guy, because then that would be a +8, right?
So we're using the top one still.
That's right. You still would use the original. You have to use Rick.
Oh, okay, okay. So 2.
Or F5.
Yeah, I was getting confused. I was still using the bottom one.
Are you sure it's 4f5?
3.
4f1.
So we did 2.
So
4f3.
there's 2 here. So that would be 2 right here.
Oh, sorry, 4F3.
Okay.
God, we're so bad at math.
Okay.
Dr. Henry, can you write, I know you did this a while ago, but you know where you have like where the S starts, where the P, where the D, and
Yeah.
where the F? I want to rewrite that on my periodic table so I don't get lost, because that's where I get lost when you go back down all the way to the bottom where the stuff is.
That is
Yeah.
the S.
Yes, okay.
This is the P.
And does the P also count that 2 up there, the helium, or no?
No, it's really because the helium is really located in the S, right? It's just because it's a noble gas, they want to line it up with the noble gases.
Okay, but we never counted with the S, right? Because we always just say S1, S2, right? Or do we?
No, we do. We count it. We say 1S right there. And then, so that's just it. So, but you don't, it doesn't count as a P. It's part of the S. So this is considered to be an S.
Okay,
So that's why I draw that line down here.
so
So
there.
this guy is really an S.
Part of an S.
Yeah.
Okay, let me
Okay.
write an S in mine too then.
And then this here is the D.
Okay.
And then this here is the F. Okay. Does that make sense?
Just the top row or the bottom row too?
Both of
Like
these.
89, 90, that's F2 or?
Yeah, these are all S. Just like all
Okay.
of these underneath here are Ds, right?
Okay.
And all of these underneath here are S's, the same way.
Except for the last two. Okay, got it.
And so,
Thank you.
when you're in doubt, right, there's also this table here.
Do you have that somewhere on the modules?
Yes, it's in the chapter 11 notes,
Okay, cool. Thank you.
and you guys can print that out. Okay, piece of cake?
Okay, cool. Thank you. Okay, yes.
Okay, good. Okay, so at this point, you guys should be very familiar with all of that, right? We've talked about the core versus valence electrons. You guys are actually ahead of my other class, so I don't know what to do. Let's see. Hold on. I'm having a little trouble with my slides there. Okay. Okay, so let's see if you guys, how good you guys are at kind of figuring things out, right? So here's a question that you might see on one of the practice tests. So, or on the test. So it says, write the electron configuration for the highest occupied level for group 6A/16. So where's group 6A? Or 16, group 16.
Can you repeat it again?
I said, where is group 16? Because here's the question.
The reactive nonmetals, the oxygen one.
Okay, so group 16 is under oxygen? Is that
Yeah.
here? Okay.
Yeah.
That's group 16.
Yeah.
So if we're writing the highest,
Yeah.
it says the highest occupied energy level for group 16 elements.
Mm-hmm.
So if we're going to write that, what is the electron configuration for oxygen?
Helium.
So it's our core.
2s2.
2p4.
2
P4.
2p4. Okay. What about for sulfur?
Neon. 3s2. 4 or 3p4.
Okay. So if we went on, right? As we went on to the next one, the key thing is this here represents our valence electrons. Okay. When we go beyond that, okay, so the next one would be selenium, right? For selenium,
Argon.
oh, and this is sulfur, and then we go selenium. Okay, so it would be argon.
4s2.
4p4.
So yes, it would be 4p4, right? But there's also the 3D that is completely full. So the 3D, because we'd write 4s2, 3d10. Let me put this in an area that you guys can see. Shift this over. Change the color. Okay, so it's argon. So it's 4s2, 3d10, and 4p4, right? But if we look at the highest energy level, which is a 4, right? We have the 4s and the 4p. These guys are what we primarily use for valence when they're above a certain level, because this guy is filling up that third energy level. Because if we wrote that, see, we had 1s, 2p, 2s, 2p. Then we have 3s, 3p, and then we have 3d. Then we have 4s, 4p, 4d, 4f. Okay, so these guys, since this guy is completely full, right? It's kind of like saying it's no longer able to be used for reacting. The only thing that's going to be able to use for reacting are the ones in that outer shell, that 4s guys. So 4s and the 4p. So when we get over here, we're really just looking at the s and the p for valence. And the p for our valence electrons. Okay. The only things that give us trouble are these guys in the middle. They screw everything up. Okay. Does that make sense?
Yeah.
Okay. And then since this is completely full, these are the only two that we're going to be using. The 4s and the 4p are the only ones that we're going to be using for reacting. Okay.
So would 100 or 116, the livermorium, would that be
Yep.
the one with the highest in group 16?
In group 16, that would be the highest. Yeah, that would be the highest. But the way that you would write this is generally, because, you know, we never know how high it can go. You'd put n for any variable.
Okay.
S2, N, P4. Okay, so that's how you would answer it.
Oh, okay.
Okay, and so it kind of understood. You were saying, okay, my 4, and then I just have these two that are going to be increasing in number. Okay, so let's see. Clear. So does that make sense? Since there's 6 valence electrons that it has, right? Oxygen has 6 electrons that it can use for bonding, right? And then those are the 6 valence electrons. Sulfur has 6 valence electrons that it can use for bonding. Selenium has 6 valence electrons that it can use for bonding. Okay, so here it says identify the group whose electron configuration for the highest occupied energy level is NS2 and NP2. So let's look at the periodic table. Did you guys write that down?
Yeah. What does N stand for again?
Remember, N stands for any variable.
Any variable. Okay,
Yeah.
thanks.
Or it's just, in that case, our any energy level. So the highest, oops, I wasn't supposed to show you the answer already. I meant to do this. Okay, so it was NS2, NS2, NP2. So where would NS2 and NP2 be? What group? Okay, that would be, this would be S, this would be P. So I'm saying I have 2 electrons in the P.
Group 4.
Yeah, so group 14, carbon.
Right. Does that make sense?
Mm-hmm.
Okay, so then it would be group 14. Okay, so if I had wrote NS2, NP2,
Group 17.
That's right.
Yeah.
Okay.
Well, these ones are fun.
Easy,
What-
right?
What's the hard part of this?
It's reading the question, right? Because most people get lost in the question and then. Okay, so. Okay, so I'm actually gonna, you guys are finished early. So what we're gonna do is I'm gonna have you guys write a couple of, you guys finished way too early. A lot earlier than the other class, though.
So does that mean that we're on a roll?
You guys are on a roll, definitely.
So can, since we finished early, do you mind going over the homework? Not number 3, not the one we're supposed to be turning in on Friday, which is number 5, because it talks about the Lewis diaphragm. When are we going to talk about that?
We're gonna talk about it on Thursday. That's why your homework may be pushed back.
Okay, so you got me stressing here.
So we can talk about that. Okay, so I can kind of give you because really all it is the next couple slide, right? The Lewis diagram. So we talked about ions, right? You guys are feeling comfortable with the ions so far? Okay, so Lewis dot structures or Lewis symbols, they're often interchanged with each other. They're going to be based upon what we call the octet rule. The octet rule basically means that you have 8 electrons surrounding you. So if we talked about oxygen, oxygen had how many valence electrons?
Two.
5.
Now remember, not electrons, total electrons. We just want the valence electrons. So if we write,
Okay.
what was the electron
6.
configuration for oxygen? It was 6, right?
6.
So it was, if I remember correctly, it was helium. It's
2s2.
2s2, 2p4.
okay. Remember, these are the valence electrons. So that means there's 6 valence electrons, right? Another way of looking at it is just counting across 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, right? In that second level. So it has 2 valence electrons. So the way that we would draw the Lewis structure for oxygen would be 1, 2, 3, 4, 5, 6. So it has 6. So the goal is to try to get 8 around you. So you're going to try to find a way of getting 8, right? But first, we just want to draw the Lewis structure. We're talking about the valence electrons. So these are the electrons that are going to be used for bonding, right? So you want to just draw those electrons around the symbol so that we can say, okay, we have 6 electrons that is capable to use for bonding, okay? Carbon. How many valence electrons does carbon have?
3.
Sure?
4, I mean.
4, okay? So the easiest way is going to that level, 1, 2, 3, 4. So we have 4 electrons that we're able to use. So we draw 4 dots, 1, 2, 3, 4. Does that make sense?
Yeah, it doesn't really matter where we place the dots.
Okay, so ideally,
Don't they have to go in pairs, Dr. Henry?
oh no, okay. So remember, the very first thing that they want to be individually, and then they want to go into pairs later on. Okay, so like here, these guys, you can put them on 4 corners. When we're starting to form bonds and everything, then you want to try to put them in pairs because everybody has to be accounted for.
Yes.
Okay. So what about nitrogen?
5.
That's right. 1, 2, 3, 4, 5. Okay. So let's see. What about antimony? Where's antimony located at? Give me the atomic number.
15.
Antimony.
85.
51.
Oh.
Anthony.
Can you point it out in the thing?
51.
Of course I can point it out in the thing. Then you know the, so it's 51, Anthony. Okay, so how many valence electrons does that guy have?
15.
5.
It has 5, that's right. So you're only gonna be accounting
Oh, you're right.
this guy and this guy, repeat,
That's-
okay? So it's gonna have 5, so it's gonna be SB, and then it's gonna have 5 electrons around. Okay,
Okay, but
Henry,
hold on.
and why do you only count 5? I forgot.
because this guy is completely full, right?
Oh, yeah,
If you
yeah.
look
Those
at it,
are
it's
the fat
completely
guys.
full.
Okay.
So we're not gonna count this. And these two, this is in the 5S, this guy is in the 5S, this guy is in the 4D. It's in a different
4D.
energy level. So it's kind of
Okay, yeah.
protected.
Okay.
Okay.
Also, Dr. Henry, so when you just made the dots right now, you made them in pairs at first, and then you put the last one.
Yeah. Like for right now, it doesn't matter because they're not bonding, right?
Okay.
As long as you get them around them, that's fine. But usually
Okay.
it's like, you know, you have them here, here, here. You have 4 spots.
Okay. It's
Right,
just
right now, right?
yeah.
Right now.
Just
But don't worry
stuff
about
like
it.
that.
We'll make it more complicated later. I promise.
okay.
Okay. So, let's see. What about the Lewis dot structure for aluminum?
3.
3.
3 dots. That's right. Okay. And beryllium, Be.
2.
2.
Okay. Piece of cake.
Piece of
Yeah.
cake. Biggest cake.
So basically,
Easy.
I can put those dots wherever I want, you said, right?
Yep.
As long as there's 2 dots or
That's
3
right.
dots.
Just for
Yeah.
right now, until then you start doing the
More complicated.
little
Yeah.
circling thing.
When we
So for
start
the
bonding.
homework- So
What
for
was
the
that?
Bonding.
So for
Yep.
the homework, it's basically just wherever.
Yeah, if you're just talking about a single element, yeah, for right now, it's wherever.
Okay.
Okay. And you guys know how to do that, like to put the dots in and all that stuff so far?
Yeah. Well, you mean what we just learned right now, the Lewis structure?
Yeah.
Yeah.
Okay. So what we'll do, we'll start talking about how things are going to be bonding. So that's really the next chapter, right? So the ionic bond, the covalent bond, and we're going to be using Lewis dot structures for covalent bonding, right? And you can use it for ionic bonding, but it's not as pretty. So, okay.
In the previous homework, there was a question about Hund's rule.
Yep.
What is that? Because it's like it's asking which one violates Hund's rule. but-
Okay. Okay. So Hund's rule basically says that, you know, that concept of where we have one that's going to go positive and one that's going to go negative. So
Mhm.
opposite directions, right?
Yeah.
So, and that's also, so remember when we talked about Pauli's exclusion principle?
Yeah.
So let me show you. Hund's rule basically says that when we're putting electrons in, and you guys really don't talk about it too much because we didn't really get into the diagrams too much, but it says that we have 1 electron. Let's say we have 3 electrons to put in here. So we have 3 electrons to put in here. So Hund's rule says that the first thing that we're going to do if we have 3 electrons to put into the p orbital is that we'd put them both in each one in an orbital, right? First, okay, before coming back in and putting another one in. So rather than doing this, we're going to put 1 in each one first. Okay, the reason why it does that, so the reason why you put 1 in each orbital first is because it forms a balance, right? If you have two of these guys here, these guys will cancel each other out. There won't be a balance in that case, right? Because they're in opposite directions, so they kind of cancel each other's out. So you're leaving this guy kind of charged up. Where if you put them one in each one first, it kind of balances all of the orbitals. Does that make sense?
Okay.
Yes.
Yeah, that's when we went and did like I remember. Okay.
Yeah.
Thank you.
No problem. So that's Hund's rule. Okay. And so Pauli's rule says that you can't have 3 electrons in an orbit, right? You can only have 2. This will never happen. Right?
Okay.